There we go. Okay. So I like to always introduce, whether it's this class, sophomore biology, senior level, organic chemistry, or A&P, when we start a new chapter, I always like to think, what comes to your mind when you see what you see here? So our next chapter, okay, work in machines. We talk about power, work, because that is an actual definition what work is. And if we're measuring an amount of work done and how efficiently it's being done, that gives us power. But you're probably not really all that familiar with power. You might associate that more with what for a lot of you farmers? Not just power, but rather what? Say that again. Oh, okay. Because I think you said what we were looking for. What did you say? Oh, okay. You didn't say horse? Oh, okay. So horsepower is one of the next aspects that you will attempt to calculate by doing an activity for that. So when we're talking about power, it's kind of a rather vague term. Like when we talk about lights, when you are looking or searching / shopping for light bulbs, they are measured in what? Do you know? Okay, there's watts, and then we also deal with this in kilowatts, okay? And that's pretty much any one of these ballast lights. You could look up there and it probably says 60 watts, perhaps. I don't know. In your house, you might not have, you might have all LED lights now, and those are also measured in watts as well. Okay, but one of the things that happens when we talk about this as far as trying to calculate horsepower for yourself, okay, it's not a lot, okay? Don't have it in your mind that, oh my gosh, I can replicate half a horsepower. That's just not going to happen. Not that you are an individual that just can't supply a lot of power. We're just not built to design, or we're just not built to supply a lot of horsepower, because when it comes to the activity that we do, we're pulling a sled. That's as simple, as simple as we could say. You're pulling a sled along, and there's a lot of weight on there. So by the time you get to the end, you're perhaps pretty tired. But tractors and machines, they don't have that problem, do they? They just continue to work and work and work, because a machine can keep on moving, where us as humans, we just begin to get tired. Even horses get tired as well. And does anyone in here deal with horses? I don't. It's just some of the experiences I think that is accurate. Even after working a horse, I think you need to go through a cool down process, maybe. I don't know if that might sound familiar, but our next course and or set of problems deal with whether we're calculating work, whether we're calculating power, or perhaps an efficiency of a machine, how much horsepower is being done, and things to that nature. Okay. In order to do work, you have to have some sort of movement in place, okay? So if you're in the weight room and you have lots of weight on there, but you can't lift the barbell, the dumbbell, or whatever it is you're trying, the kettlebell, maybe, does that sound right? Or is it just called a kettle? I'm just asking because I'm not sure. It is a kettlebell? Okay. Bell, not ball. Kettlebell. Okay. So if you can't move that kettlebell, no matter how hard you are pulling on that, you are not doing any work. Because if it does not move, you are not doing work. Does everyone have this content that wants it? Okay? Well, we're still writing, but for those of you who are done, I want you to think about why are you not doing any work on your books? I don't think you have to write all that out. At least I'm thinking, since this is such a long aspect, that we're taking some of this content here. So why are we not doing any work on your books? What did we say earlier with the kettlebell? No matter how hard you pull on the handles of that kettlebell, I always want to say ball, on that kettlebell, why did we say you're not doing any work on it? What has to occur for work to be done? Yeah, it has to move, because that's what it says here, okay? Work, a force present, and that force makes an object move. So if it's not moving, you are not doing any work on it. So then, come on here. Okay, so then why are we not doing any work on your books? They're in your backpack, right? So why are you not doing any work on your books? What are they doing in your backpack? Say that again. They're not moving. At least maybe they might be moving around a little bit because maybe your backpack is a little too big. But if it is not moving, you're not doing any work on those books. Okay? Now I understand those are, let's say, it might be confusing aspects of the definition. Okay? Because I'm willing to think that when I changed one of my backpacks on here, I just happened to see this in one of these side pockets on here. For anyone, and we'll make sense of this because we're saying this, you say, doesn't make any sense. Well, some of the definitions that we use maybe in science, even in sports, you might say, don't make any sense. Okay? Because how many basketball people do we have out there? Okay? So if a loose ball is rolling out on the court, you as a player jump on it and you slide for 6 feet. The most common response that the crowd might say is what? Is that a travel? Is it? So you jump after a loose ball. You have the ball cradled up next to your abdomen, but you go sliding on the floor about 4 to 6 feet. That's a travel? Okay. Well, and everyone's coming up with a consensus that that is a travel. Okay, and we're just asking a simple question here. Okay, so this comes from basketball officiating. This is one of the things that you could possibly partake in as well. And let's see here. Quick guide to common basketball rules and misconceptions. Okay, this comes from, I'm guessing, the state of South Dakota. Okay, number 5 here, traveling. Okay, the traveling rule is one of the most misunderstood rules in basketball. To start a dribble, the ball must be released before the pivot foot is lifted. On a pass or shot, the pivot foot may not be lifted but may not return to the floor before the ball is released. A player may slide on the floor while trying to secure a loose ball until that player's momentum stops. At that point, that player cannot attempt to get up or roll over. A player securing a ball on the floor cannot attempt to stand up unless the player starts a dribble. A player in this situation may also pass, shoot, or call timeout. If a player is flat on his or her back, that player may sit up without violating. It says nothing about traveling, does it? It says you can slide on the floor, and that is not a travel. So sometimes some of the misconceptions that we see maybe in science or even in athletics, the definitions are maybe way more specific than what just the general, let's say, answer could be. Your books aren't moving. If they're not moving, you're not doing any work on them. If you slide across the floor, you are not traveling unless you do what? Unless you try to stand up. Okay? So I just happened to notice that this morning. I thought maybe we would think that was kind of neat or unique, or because I think a lot of you do play basketball in here. Okay. All right. Now, what the author goes on to talk about is energy is part of chapter 4. But in what I think is best for us, we move on to chapter 5 and talk about work, power, and work and power. And then we end the semester with that of energy. But it certainly would perhaps make sense when we're talking about this amount of energy if you have, let's see here, just have to use your imagination. I guess if you had a ball and you hold it at hips, at the height of your hips, you let it go, it may bounce almost back up to your hip. So what happens if you raise and you hold the ball above your head and let it go? Is it going to bounce higher than your waistband of your hips? Why would you're nodding your head? Yes. Why would that be accurate?
Because it has more potential energy.
Yeah, because it has more energy into it. That's right. Okay. So let's see where that puts us. Work and energy, power. Okay. I just want to do, once we get down to here, we'll be done for today with just this part because we can calculate work. There is a new formula for that. Okay? So on your formula sheet, I would highly suggest that you write that down. One comment I meant to make, I saw it up there, and then I kind of got off task, or, oh, it's not up there. Okay. What is it that we use? What do farmers use for harvesting? What's it called? A combine. Okay. It would be my interpretation, one of the reasons that we call it a combine, and I think it maybe makes more sense with combining beans, okay? So for anyone who knows anything, yes, it does. We'll get to that in just a moment, okay? So for anyone who knows anything, how do beans get harvested? I mean, they just don't flow into the combine, okay? What has to happen first? It's at the base. You have this, I think it's just a, kind of looks like a carousel that moves around. That just helps feed the beans into the head. But what's happening right next to the ground? Does anyone know what those things are called? Okay? And we're not testing on what those are called. We have these deals that move back and forth at the base of the combine. Has anyone ever seen a combine head before? Okay? So what we are looking at, okay, not that. Okay. Yes, it's kind of like you can use optical illusions with chess and checkerboards, okay? And then there's a little bit of a space. Now, you don't need to be drawing this if you think, oh my gosh, we're spending time on this, maybe we should write it down. I'm not the best artist, but for anyone who's ever seen a bean head before, okay, those are called sickles that they move back and forth. It's actually based off, I think it was John McCormick's Reaper that invented this years ago to harvest wheat, oats, things like that. Something you'll probably talk about in American history. But as these are doing one sort of motion going back and forth, that cuts the beans off, they fall down, and that, I believe it's that rotating drum. If I was asking some of the older students, and maybe some of yourselves, that everything you're talking about, that is totally inaccurate how a combine head works. But it's my interpretation. You cut it. That carousel motion, that helps feed the beans into the head after they've been cut. Then once it flows through the head, there's a type of drum, I don't know what you call it, but it vibrates back and forth like this. And then what comes out the back end of the combine? Do we know? Stems, pods, everything that you don't want. So what happens is you're taking one motion like this, and then the interior part of the combine is another type of motion that does work. You put the two together and you combine them. That's why I believe we know it now as a combine, because it takes two types of motions, puts them together. Now we call it a combine. All right. Yeah, it's one of them aha moments, right? Okay. You can say W. I would not use a capital W, okay? So W is for work, and that equals a force times a distance. And then typically, from prior knowledge, forces are measured in what? Newtons. This is going to be measured in meters. So then a derived unit, okay, that means you're putting two things together and combining them. A Newton and a meter. You multiply these two and you get what we call a joule, okay, named after 18th century physicist James Joule, I believe, okay? So you take a force times a distance, you get an amount of work done measured in joules. Okay. Not done. We'll say completed. Okay, so some of you are wrapping this up by writing the problem down. Maybe some of you already have that wrote and or written down. So you've read it. What's the next thing that you should do? Write down the information that we know. Okay? So what do we know in this problem? What, winter's coming? That might be a conception about Saturday. If you believe the weatherman. Okay, so force equals 18 newtons. Okay? What else do we know? Okay, and that distance is what? Okay, now, how many of you might be looking at that and saying, that does not sound or appear to be a great distance? 0.21, that can't be very far. Is that possibly what you are thinking? The reason we say that is, okay, if that's a meter stick, okay, approximately 0.21 meters is that, if this is a half, I don't know, we could get a meter stick out, but we're just eyeballing this. If this is a half a meter, what is half of a half? A quarter, okay? So then half the distance there to here, okay, say is about right there. So if this is 0.50, what is a quarter then? 0.25. So here we're about pushing your shovel only about this far. Okay? So one of the things that might take place with that is you might say, why are you only pushing it for that amount of a distance? Well, there could be a variety of reasons. One, maybe it's really heavy snow. Two, maybe there is ice frozen underneath and you just can't push it very far. But in this case, is work going to be done? And how do we know that work is going to be done? Because it moved. If we have movement, we know that work will be done. Because if we wanted to be mean and say, if you're pushing with 18 newtons, but the shovel does not move, how much work are you doing? None, because there has to be movement for work to be done. So extrapolating that, let's see here, 9, 4.5. So what is it, 4 something? 3.78. Okay. So to do this, work equals 18 times 0.21. So work equals 3.78. And how do we label that work? In joules or J. Okay. So what could also happen is we could okay. So, and I might just be guessing over here. Are we distracting for other people? No? I hear a lot of commotion over there, more over here than I do on this side. I'm just guessing. Maybe we're just getting old. All right. My apologies. Okay. So when we look at this, maybe we are given something in joules, and we give you the distance. If we give you a mass, okay, you can maybe solve for the acceleration by finding the force. Because in this formula, you have to know how many variables. You had to know 2, right? And we did. Here's 1, here's 2. But one of the things keep in mind is we can break this further down, because what does force equal? Mass times acceleration. Okay? So it could be such an aspect to where we might break this further down. And why would we do that? Well, we are teaching you to be critical thinkers, problem solvers, having a good work ethic, all of those hopefully rolled into one, so that when some of you decide to take the ACT test, maybe that's not for everybody. Okay? We want you to be critical thinkers and or problem solvers. All right. Front row, are we good? Everyone's second row, are we good? Third row. Third row. Okay, everyone's nodding their head yes, so we will catch up to you next time.